All right, so you know those RNNs, right? Recurrent neural
Yeah.
networks. Well, today we're going deep on them, specifically on a cool new technique called test time training.
Or TTT for short.
Exactly.
Yeah.
And you know what's really cool about this? You actually sent over this awesome research on TTT,
Yeah.
and it's really pushing the boundaries of AI.
It's some really cutting edge stuff. The paper we're looking at is called Learning to Learn at Test Time, RNNs with Expressive Hidden States.
It's a mouthful.
Yeah, it is, but trust me, it's worth it.
So, okay, so RNNs, I feel like we should set the stage a little bit for listeners who aren't, super familiar
Yeah, for sure.
with them. They're like the marathon runners of deep learning.
That's a good way to put it.
They can handle these sequences of data like text, time series,
Mm.
but they kind of have a weakness
They do.
when it
Yeah.
comes to really, really long sequences.
Exact. You see, traditional RNNs, they have a hard time remembering information from the very beginning of a sequence.
Oh, so it's like when you're in a really long lecture,
Exactly.
and by the end, you forget what was said at the beginning.
That's a perfect analogy.
Yeah.
And this limitation of RNNs, it really became clear in that OpenAI scaling law paper back in 2020.
Oh, yeah, I remember that one.
Yeah, and they found that LSTMs, that's a type of RNN, they just couldn't keep up with Transformer when it
Yeah.
came to, using that long context effectively.
And there was also that other RNN, Mamba.
Oh yeah, Mamba.
It scales pretty well,
Initially, yeah.
but it eventually hits a wall,
It does.
unlike Transformer.
Yeah. And this all boils down to a fundamental constraint. You see, RNNs have to pack a ton of information into a fixed size hidden state.
So it's like trying to fit, I don't know, an entire semester's worth of notes on a single sticky note.
That's a great analogy. There's just not enough space.
Yeah. So it's not that RNNs are just bad at long context.
Right.
They're playing a game with like a major disadvantage.
Exactly. And that's where this super cool idea of test time training layers comes in. So TTT, it basically changes the way we think about the hidden state. Instead of being this static container with limited capacity, TTT turns it into this dynamic model
Oh, wow.
that can actually learn and adapt as it processes the sequence.
So it's like we're giving our RNN a superpower.
Exactly.
Yeah.
It's like instead of just passively taking notes in a lecture, you're actively engaging with the material. You're making connections. You're building your own understanding. As the lecture goes on.
So the hidden state is like our notes that are constantly being like rewritten and
Yeah.
refined as we learn more.
That's the idea. And the engine behind all this continuous learning is something called self-supervised learning. You've probably heard of this. It's been incredibly successful with those big language models, the LLMs.
LLMs, yeah. So it's like we're taking all the knowledge from a massive library
Mhm.
and like compressing it into this small personalized guide.
I love that analogy. That's a really good way to put it. So with TTT, each input in the sequence acts as a mini training example for the hidden state model. And that allows it to kind of adapt and fine-tune its understanding with every step.
That is cool. This is like blowing my mind a little bit.
Yeah.
But okay, if we're essentially training a model during test time,
Yeah.
wouldn't that make things really slow? Like significantly slower?
That's a great question. And, the researchers obviously thought about that too. They came up with some really smart techniques to make TTT surprisingly efficient. So one of them is called mini batch TTT.
Mini batch, okay.
Instead of updating those hidden state weights after every single input, they process the inputs in small batches.
So it's like dividing the workload
Exactly.
and conquering it faster.
Exactly. And then there's another technique called the dual form for calculations.
Dual form.
And this basically rearranges those math operations to take advantage of parallel processing.
Okay, so we're talking about like serious optimization here.
Mm.
Does this actually lead to real speed improvements?
It really does. They actually explored two types of TTT layers. One is called TTT-Linear, which uses a simple linear model. And the other one is called TTT-MLP, which uses a two-layer MLP. And get this, with these optimizations they put in place, TTT-Linear actually becomes faster than Transformers for long context lengths.
Wait, hold on. Did you just say faster than Transformers?
I did.
Wow.
It really does challenge some of those assumptions we had about, RNNs versus Transformers.
That's incredible. Okay, so we've got this connection to Transformers now
We do.
with TTT. But remember how we talked about TTT using that self-supervised learning?
Yeah.
Like the big LLMs are trained on?
Right. Well, this is where things get even more interesting, and the lines between different models really start to blur.
Oh,
Because it turns out a specific configuration of TT-linear
okay.
is actually mathematically equivalent to linear attention.
Oh, way.
Yeah, which is a key part of transformers.
So it's like we found a secret passage
I know.
between these two worlds of
Oh.
RNNs and Transformers.
It's amazing, right? It shows you just how connected all these different areas of AI research really are. And sometimes the most innovative solutions come from really just rethinking our assumptions.
That's wild. Okay, so we've only scratched the surface here, right?
We've only just begun. There's so much more to uncover.
Oh, man, I am so ready for more.
I'm excited to share it with you.
Let's do it.
All right. Welcome back. I hope you guys are ready for more because things are about to get even more interesting.
Oh, I'm so ready. My brain is already like buzzing from that last segment, but I'm totally ready for more.
Well, good, because we're going to unpack those connections between TTT and Transformers even more.
Okay, let's do it.
You know, remember how we were talking about certain configurations of TPT actually acting like linear attention?
Yeah, that blew my mind.
Yeah, and it's not just like a casual observation, you know?
Yeah.
The paper actually goes deep and gives this rigorous mathematical proof showing how those two things are equivalent.
Really?
Yeah, so like if you take a TTT linear layer and you use batch gradient descent to update it,
Okay.
and you set the learning rate to 12 and you start with 0 weights, it becomes mathematically identical to linear attention.
No way. It's like they're the same thing, but just like dressed up differently.
Exactly. Two paths leading to the same destination.
Yeah, that's wild.
And the best part is they actually tested it, you know? They implemented both TTT linear with those specific settings and a super optimized version of linear attention.
Oh, cool.
And guess what? They got the same performance.
Wow. So it's not just theory.
Yeah.
It actually works in practice.
It's crazy, right? It's like finding a secret doorway between two rooms that you thought were totally separate.
That is a perfect way to put it. Okay, so we've got this concrete link between TTT and this key part of Transformers. What else is there? Like, is that it?
Oh, there's more. Remember how we said TTT isn't limited to just using linear models?
Yeah, the possibilities seemed endless.
All right. Well, the researchers took it a step further. They decided to try something called the Nadaraya-Watson estimator as that inner loop model in TTT.
Nadaraya-Watson estimator.
Yeah, it's a bit more sophisticated than just a simple linear model.
Okay.
It's a non-parametric method. And get this, when you plug the Nadaraya-Watson estimator into a TTT layer with the right settings, it becomes equivalent to self-attention.
Hold on. Self-attention, as in the heart of what makes Transformers so powerful.
The one and only. And this is not just like speculation or wishful thinking, okay? It's backed by mathematical proofs. They did all the testing. It's all there.
Wow.
It's like we've cracked the code and found out that RNNs with this TTT twist can tap into that same power that made Transformers so dominant.
This is like completely changing the way I think about these models. It's not about one being better than the other. It's about understanding these connections.
Exactly. Yeah.
And maybe we can like combine the strengths of both.
I think you're spot on. And this paper is really just the beginning. It lays the foundation for a whole new way of thinking about sequence modeling, deep learning, the whole thing.
I'm already getting excited about the possibilities.
Yeah.
Okay, but before we get too carried away, let's talk about those optimizations again.
Yes. Practicality is key.
Right. You mentioned that the researchers came up with ways to make TTT actually work efficiently.
Yeah, they did. Remember how we talked about how training a model during test time could really slow things down? Well, they addressed that with two main things.
Okay.
The first one was, remember, mini-batch TTP.
Mini-batch TTT, yeah.
Instead of updating those weights after every single input token, they process those tokens in batches.
Oh, right.
And that allows them to do those calculations in parallel, making things much faster.
So it's like, I don't know, sorting a giant stack of books one by one versus sorting them in smaller stacks at the same time.
Exactly. It's so much more efficient that way.
Right. Okay, and what was the second thing?
The second one is called the dual form. It's a bit more technical.
Okay.
But basically, it's about rearranging those math operations to make better use of modern hardware. You know, like GPUs and TPUs that are built for parallel processing.
We're like optimizing the recipe so we can cook multiple dishes at the same time.
Exactly. It's all about maximizing efficiency, making the most of what we've got.
I love it. Okay, so these optimizations, they actually make a real difference.
Oh, absolutely. They did experiments on CPUs, GPUs, the whole shebang.
Wow.
And saw big speedups. Actually, on a TPU, TTT-Linear was 10% faster than a standard transformer.
No way.
Yeah, per iteration, that is, in terms of training speed.
That is impressive. And you said they haven't even fully optimized everything yet, right?
They said there's still room for improvement, especially in optimizing something called the backward pass.
Backward pass.
That's another area they're looking into.
So this isn't just about making things work in theory.
Right.
These optimizations are making TTT a real contender for real-world applications.
Exactly. It's not just an academic exercise. It's about building tools that can actually solve problems.
Yeah.
And pave the way for this new generation of sequence models.
This is so cool. I'm loving this deep dive.
Me too. It's exciting to explore these ideas.
Okay, so where does TTT go from here? Like, what are the researchers looking forward to?
Well, one thing they mentioned was pushing the limits of context length.
Okay.
You know, their experiments were limited by the hardware they had, but they're imagining TTT being used to process sequences of millions or even billions of tokens.
Wow, billions.
Yeah. Think about that, analyzing like an entire library's worth of text in one go.
That's mind-blowing. What kind of models could even handle that?
They suggested maybe using convolutional neural networks, CNNs, as that inner loop model within TTT.
Oh, I see it.
Because CNNs are really good at handling a lot of data efficiently.
Right.
So combining them with TTT could open up some crazy new possibilities for understanding these super long sequences like text, video, even the data from a robot moving around in the world.
The possibilities are endless.
It's really exciting. We could be analyzing years of stock market data, understanding historical events, even modeling how languages have changed over centuries.
That's so cool.
And there's even more. They also talked about something called multi-level learning to learn.
Multi-level, okay.
Remember how TTT can be used with self-attention?
Yeah.
Well, imagine if that inner loop model itself was a self-attention layer.
Whoa.
Yeah, it's like models within models all learning and adapting.
It's like the inception of deep learning.
That's a great way to put it. It points to a future where our models are less about these rigid architectures and more about dynamic, evolving systems that can learn and adapt to anything we throw at them.
That is a future I am totally here for. It all comes back to this idea of learning to learn at test time, right?
It does.
We're breaking down those walls between training and inference and embracing this idea of continuous learning.
That's the heart of it. And it really makes you think about how we learn as humans, doesn't it?
It does. Okay, so this paper has been amazing. It's challenged the way I think about everything.
It's been a wild ride.
I'm so glad we did this deep dive.
Me too. It's been a pleasure.
Okay, should we wrap things up and talk about some final takeaways?
I think that's a great idea. Let's do it.
Welcome back, everyone. I hope your brains are still firing after that last part.
I know, mine is.
Because it's time to bring it all home and talk about some key takeaways from this deep dive into test time training.
I'm ready when you are.
Okay, so for me, one of the biggest things was realizing that RNNs, they're not out of the game when it comes to long sequences.
You're absolutely right.
You know, we started this deep dive talking about the challenge they face, that bottleneck of compressing all that information into a tiny hidden state.
Right.
But TTT, it's like a whole new way to think about the problem.
It really is. We're not treating that hidden state as a static thing anymore. It's a dynamic model. It's constantly evolving.
Yeah, it's like giving the RNN this upgrade. Like, it can learn and adapt as it goes.
Exactly.
And speaking of learning and adapting, those moments where we talked about TTT being mathematically equivalent to attention mechanisms in Transformers.
Yeah.
Those were like mind-blowing for me.
They were pretty incredible, weren't they? I mean, who knew that these two seemingly different areas of AI could be so connected?
Right. And it makes you think about how much more there is to discover.
Absolutely.
And let's not forget about those optimization techniques.
Oh, yeah, those are crucial.
Any batch TTT in the dual form.
They made TTT actually practical, right?
Exactly. Without them, it would just be a cool idea, but not something you could actually use.
Exactly.
Okay, so thinking about the future.
Yeah.
I can't help but get excited about what's next for TTT.
Me too.
We talked about using convolutional networks with TTT to handle those super long sequences.
Right. Millions or billions of tokens.
Yeah, and then multi-level TTT with all those nested layers of learning.
Models within models.
It's great.
It's like the future of AI is all about these dynamic systems that can learn and adapt on the fly.
And it all comes back to this idea of learning to learn at test time.
It does.
We're changing the way we think about training and inference.
Right. It's not about separating those two anymore.
It's about continuous learning.
Yeah.
Always evolving.
That's a great way to put it.
And you know what's really cool?
What?
The researchers actually wondered if TTT could be a model for how humans learn?
That's a really interesting question.
Because we don't learn from these perfectly organized data sets, right?
No, we don't.
We learn from experience,
Yeah,
and we're constantly adapting and refining our understanding of the world.
exactly. So maybe this research on TTT can teach us something about ourselves, too.
That would be amazing. Okay, so I think that's a great place to wrap things up.
It is.
This deep dive has been a wild ride.
Yeah.
We've explored so many cool ideas, challenged our assumptions.
And hopefully inspired some of you listening to go out and learn even more.
Exactly. The world of AI is constantly changing. There's always something new to discover.
So keep exploring and keep those brains buzzing.
And thanks for joining us for this deep dive. We'll see you next time.